This is part 3 of Unit 5, Lesson 4, Concavity and Second Derivative Test. So in this final video, we are going to use the second derivative to test for extrema of our function. So similarly, the second derivative is the first derivative of f prime of x. So the same relationship that exists between f and f prime also exists between f prime and f double prime. So to save us some time, since we're already using the second derivative to find the concavity, we can use the second derivative test as an alternate method for finding our relative extrema. The only exception to this would be if a relative extrema is also an inflection point. You're not going to have either a positive or negative sign of your second derivative. It'll be 0. So the test fails, and you'll have to go back to the first derivative test because something else is happening there. So just to summarize everything in a table, if x equals c is a critical number of f of x, then f prime of c equals 0, or f prime of c does not exist. That's what it means to be a critical number of the function. This makes x equals c a possible maximum or minimum value of f of x. So what we know is if our second derivative is positive, then that means our function is concave up, and it also means that our first derivative is showing an increasing section of the graph because its derivative is positive, which means its slope is positive. If our second derivative is negative, then f of x is concave down, and that means that our derivative is decreasing. So that means we're decreasing towards an extrema, so it would be a minimum. And if it's neither positive or negative, which means it's 0, that would be a possible point of inflection, as we saw in an earlier video where we had a 0 for the second derivative, but we didn't have a max or a min. And in this case, this is inconclusive. So it is a possible relative extrema. Okay, so let's put this into play here with some examples. All right, so example 7. Use a second derivative test to find the relative extrema of each function and justify your result. So we are going to start by taking our first derivative. So g prime of x is going to be 4x to the third minus 24x squared. Now what we want to do right here is we need our critical numbers, so we're going to find our zeros. And so we have two critical numbers. We have 0 and we have 6. Okay, so let me just label those as our critical numbers, so we keep track of everything. Okay, then from there, we're going to take the second derivative. And we get 12x squared minus 48x. And now we're going to set that equal to 0. And we get, so we might have a little problem here with that number. All right, so now how we use this is we are going to substitute our critical numbers into our second derivative. So our two critical numbers are, let me just cut this chart in half here because we have 2. We have 0. And we have 6. And so we're going to substitute them into the function. So when we do that, we get, there we go, 0 minus 0 minus 5. So we have a negative 5 here. And when we substitute 6 in, we have 6 to the 4th minus 8 times 6 to the 3rd minus 5. And when you do that, I did the arithmetic already, negative 437. And then we are going to substitute our critical numbers into our derivative. So when we do that, our second derivative, so we get 0 here. And when we substitute 6 in, we are going to get 72 times 2, which is a positive number. We don't need to know exactly what it is, but it is positive. All right, so in this case, what we find out are conclusions. Our first, we have a local minimum at 0, comma, well, I'm sorry, our minimum's at 6 comma negative 437, and the reason for that is that our second derivative is greater than 0, so that would mean our function is concave up. Oh, this is actually g. And the second thing we found out was we can have no conclusion at x equals 0, since g double prime of 0 equals 0. So what that means is you would have to go back and make yourself a little sign chart here and just test your 0. So here is negative 1 and here is 1, and you'd have to check. So if you put negative 1 in your derivative, you'd have a positive times a negative. You would have a negative number here. So the function is decreasing. And if you put 1 in, you'd have a positive times a negative. It would also be a negative. So you have no relative extrema at x equals 0. But using the second derivative test, you wouldn't have a conclusion. Okay? So that's why you have to be careful about that. All right, next example. Now we're doing the function f of x equals 1/2 x minus sine x, and we're going from negative 2 pi to pi. So we're going to find our first derivative. It's going to be 1/2 minus cosine x, and we're going to set that equal to 0. And so we're looking for where cosine x equals 1/2, and that would be, remember we're doing negative 2 pi to pi, so there are 3 values, negative 5 pi over 3, negative pi over 3, and pi over 3. Okay, and then taking our second derivative, we would get the half would go to 0, and we would get sine x. And so that's real simple. So we're going to find f double prime of negative 5 pi over 3, f double prime of negative pi over 3, and f double prime of pi over 3. Negative 5 pi over 3 would be in the first quadrant. Negative sine negative pi over 3 is in the fourth quadrant, and sine of pi over 3 is also in the first quadrant. So we get square root of 3 over 2, negative square root of 3 over 2, and square root of 3 over 2. I just did those over there just to so you can see where I got the numbers from. I didn't do that in the first one, but it was a polynomial. I figured you guys could see how to substitute in. Okay, so our 3 zeros are negative 5 pi over 3, negative pi over 3, and pi over 3. So I didn't substitute those in the function, but if I were to do that, I would get, for the first one, negative 5 pi over 6 minus square root of 3 over 2. And for the next one, I would get negative pi over 6, and then plus the square root of 3 over 2. And then finally, the last one would be pi over 6 minus the square root of 3 over 2. So I have the values of the derivatives here. I'm going to use a different color. Of the second derivative, so I can see their signs. Okay, so we have a positive here, a negative, and a positive. Okay, so our conclusions. Number 1 is we have two local mins, because we have two places where the graph is concave up, here and here. So one is at negative 5 pi over 3 comma negative 5 pi over 6. Whoops, that's minus the square root of 3 over 2. And the other one is at pi over 3 comma pi over 6 minus the square root of 3 over 2. And my reasoning is, since f double prime of x is greater than 0 at x equals negative 5 pi over 3 and pi over 3, and f is, of course, excuse me, f is concave up. So we can just kill two birds with one stone here. And my second conclusion is that there's a local max where we are concave down right here. And that is at negative pi over 3 comma negative pi, whoops, that's to be a square root, it's supposed to be a pi. Negative pi over 6 plus the square root of 3 over 2. And my reasoning for that is that f double prime of negative pi over 3 is less than 0, so f is concave down. So you can see how these go together. Okay. So, moving on. Now we have number 8. The graph of f prime of the derivative function is shown. Remember, that's the derivative, not the function. On what open intervals is f increasing, and justify. Okay, so just to mark this up a little bit here, what we know is that before a, f prime is greater than 0, and that between a and b, f prime is less than 0, and between b and c, f prime is greater than 0, and after c, f prime is less than 0. Okay, so where are we increasing? It's where f prime is positive. So we're increasing from negative infinity to a, and also from b to c, since f prime of x is greater than 0. At what values does x have a local minimum or maximum? Justify. That's going to happen at my zeros. So I have 3 zeros here. And you want to look at how the graph of the derivative is changing sign. So here we're going from a positive to a negative. So that would mean the graph would look like this. The graph of f would look like that, going from positive to negative. So we have 2 local maxes. At a, and this happens again at c, because the derivative is starting positive. It's going from positive to negative here, so it's going to be the same behavior. And the other local max is at x equals c, and the reasoning is, since f prime of x changes sign from positive to negative. Okay? and then state any inflection points, justify. So looking at the graph before I move that, there are 2 inflection points. They are going to be the zeros of the derivative. So we have a 0 here. So this is going to be f double prime of x is going to equal 0. Actually, I can put a 1 in there because we know the value. And also right here, f double prime of 3 also equals 0. So we know where the inflection points are. They're going to be the zeros of the second derivative. So my inflection points are at -1, -3, and 3, 2. And the reason for that is that f double prime of x is going to equal 0. On what intervals is the function concave up or concave down? So f is concave up on -1 to 3. It's going to be in between our inflection points there, because the second derivative is going to be greater than 0. And showing you that on the graph, you can see that right here in this stage, the slope of the tangent line here of our derivative is positive. So we have a positive second derivative, so that means that we are concave up. And we can use the same rationale, when use the same rationale for concave down. So f is concave down on -infinity to -1, and then again from 3 to infinity. And the reason for that is the second derivative is going to be 0. Okay, assume that f of 0 is 0. So we have a point right here. See if you can sketch the graph. Okay, so here's what we know. Here's our A, way over here. Here's our B, and here is C. And we know that we have a max here, and we have a max at C. And we also know we have a minimum at B. And then we have inflection points at 1 and at 3. Okay, so this graph is going to look like this. This has to come up, come to my maximum, and that's going to be about halfway, and then it's going to come down here pretty sharply, and then again this point, which is 3, 2, when I get to 2 up here, has to be about halfway. So this is going to be a little higher here, because let me erase that a little bit, because the halfway point up this side has to be at like 2. So C is going to be a little taller up, and then it's going to turn around like that. So that's what the graph's going to look like. There is one problem left in this section. I want you guys to give it a try, and then we will go over it in class, because I don't want this video to be too long.